bonding, part 3. Now, what we're going to do is we're going to look at the shapes of some common molecules. Remember, if I use the word molecule, that means covalent. Okay? So if we do F2, which we looked at before, fluorine has 7 valence electrons. It's going to share a pair of electrons with another fluorine atom. This is a nonpolar covalent bond. The molecule is nonpolar. This molecule is symmetrical. It's linear. If you were going to do the structural formula of this thing, it would look like this. Fluorine is linear. Let's do another molecule. Let's do water. Water is made up of 2 hydrogens and 1 oxygen. How many valence electrons does oxygen have? Oxygen has 6. 1, 2, 3, 4, 5, 6. How many more electrons would it like to have? It would like to have 2 more so that it can have 8 valence electrons. Each hydrogen is going to share one of its electrons. Okay? Here's going to be the shape of the water molecule. Okay? This happens to be bent. Water is a bent molecule. It is not symmetrical. This is a polar covalent bond, and the molecule is polar. Water is one of the most polar molecules out there. Now let's draw the picture, the structural formula. There it is, that lone pair of electrons. Okay, this is the Lewis structure. This is the molecular formula. This is the structural formula. Now, if we look up the electronegativities, if we do a review, and we look up the electronegativities of oxygen and hydrogen, we're going to see that oxygen has a much higher electronegativity, which means the electrons are going to be closer to it than to the hydrogen. Okay? That means the oxygen is going to have a partial 2 negative charge. The hydrogen is going to have a partial positive on each end. Because of the bent shape, and it's not symmetrical, and the fact that water is a very polar molecule, there's something called hydrogen bonding. Okay? That's when the partial negative end of the water molecule gets attracted to the partial positive end. Hydrogen bonding is responsible for the high boiling point of water. Okay? So there's a water molecule. Okay, let's do ammonia. Ammonia is NH3. Ammonia is made up of nitrogen that has 5 valence electrons. It would like to have 3 more. So in comes the hydrogen. Nitrogen thinks it has 8 around it. Oops, I forgot that pair right there, didn't I? Okay? And then each hydrogen thinks it has a pair of electrons. Okay? So right now, this ammonia molecule is very happy because the nitrogen thinks it has 8, each hydrogen thinks it has 2. Again, the electrons are being shared unequally. So the nitrogen has an apparent -3 charge, partial positive, partial positive, partial positive. This molecule is not symmetrical. The shape of this thing is pyramidal. Pyramidals are never symmetrical. So pyramidal molecules are always polar molecules. Okay? Ammonia is also going to have pretty strong hydrogen bonding associated with it. Okay, let's do another one. Let's do methane, CH4. Carbon has 4 valence electrons. Each hydrogen is going to share it's 1 valence electron. Carbon is going to think it has 8. Each hydrogen thinks it has 2. Now what's really interesting about this molecule is the shape of it is tetrahedral. Tetrahedrals can be symmetrical if the 4 atoms around it are the same. So because there are 4 hydrogens around it, this molecule is symmetrical, and as such, the molecule is nonpolar. What's the attraction between nonpolar molecules called? It is a type of van der Waals called London dispersion forces. London dispersion forces. Fluorine is also attracted to other fluorines because it's nonpolar by London dispersion forces. Okay, so what is it that I need you to know? Ready? Nonpolar molecules. The attraction between nonpolar molecules is called London dispersion forces of attraction. They're very weak. Okay? The things that can be symmetrical or nonpolar are going to be your linears and your tetrahedrals. Your other 2 shapes, bent and pyramidal, are never symmetrical. They're always going to be polar. Okay? So these are called polar molecules, and the attraction between polar molecules is called dipole-dipole attraction. But there's a special kind of dipole-dipole attraction called hydrogen bonding. And hydrogen bonding occurs in these 3 molecules: hydrogen fluoride, water, and ammonia. The attraction in hydrogen bonding is much stronger than that for London dispersion forces, which is between 2 nonpolar particles. The end.